hide it. All right, so we've done this conceptual, so this is a bit of a review, and then we will build on it mathematically. So it's thermodynamics. It's the study of heat and its relationship to mechanical energy. What's missing here is the molecules. So it's the mechanical energy of molecules. So what's heat? What's mechanical energy? We know something about mechanical energy already, right? So it's a combination of kinetic and potential energies of the molecules. Kinetic energy, energy of motion related to speed for a given mass. So we got that, but what's the potential energy within the context of molecules? It's not related to height, guys. Gravitational potential energy is, but the mechanical energy of the molecules is not. So if that's the case, what is it related to? So that's something that we will have to kind of focus on. Heat, we kind of know what heat is. Heat is a form of energy, right? So kind of definition of heat, it's a form of energy that flows from hot to cold. Just remember that. If there's temperature difference, there's heat flows. So heat is a form of energy that flows from hot to cold. So what's the relationship between this energy and the kinetic and potential energies of the molecules? So that's the subject of thermodynamics. That is the subject of thermodynamics. Evidently, we will just jump in out on this computer.
Miss Betsy, welcome home.
Thank you, Warren.
How's your bacon? You a sweet bacon? I got it.
Yeah, Warren. My vacation was fine. Thank you.
Yeah.
How's everything with the house?
Great. The plants watered, mail ordered, newspaper stacked so neatly, just might blow your mind.
Terrific. Warren, what's with the towel?
I couldn't find a red carpet.
Huh. Here.
Oh, yeah, okay.
Thank you so much.
Oh, I got it. Good. Honest, man. Hey, need me to stay overnight and help you reorient yourself to your surroundings where I could run out, grab a bottle of Merlot, and whip up some sizzling fajitas, or...
Why is it so cold in here, Warren?
Oh, I turn off the heat.
It's the middle of the winter. You can't shut off the heat.
Why not?
Because, Warren, if you turn off the heat, the pipes may freeze.
I wonder if that's what happened here.
Okay, so when the pipes freeze, the pipes will obviously burst open because of the water inside, right? So when the water freezes into ice, somehow it expands. Most things usually shrink except for water, so why does the water expand? Speaking of expansion, what's wrong with this trapezoid? It's fairly obvious, right? So the expansion was not factored in when it was really, really hot outside. And roads do have these expansion slots. If you've never seen them, now you have, obviously. So what's the purpose of it? Well, the purpose is fairly obvious in the title. So you're accounting for the expansion. So how do you account for the amount of expansion that you need? All right, this design did not factor it in, but this design did. So how do we figure out how much of an expansion that we have to factor in for our design? All right, so the temperature is the measure of how cold or hot something is. That's the commonsensical definition that I myself came up with. Yeah, go ahead. Yeah, so never mind. Okay, so the commonsensical definition of temperature is how hot or cold something is. This is a measure of how hot or cold something is. So you do the measurement using a thermometer, obviously. All right, so we got different thermometer scales in the United States. In the world, in the United States is a Fahrenheit scale. Outside of the United States, it's the Celsius, and inside is the Kelvin scale, right? So what's the purpose of measuring temperature? All right, don't write down the book definitions of it. I'm just giving you guys the sort of definitions that you would remember forever. Number one, the whole thermodynamics is related to heat. What happens to heat? Heat is energy, right? So what causes heat is the temperature difference. All right, so if there's any sort of temperature difference, the heat is going to flow from hot to cold. Okay, so that's the story. I'm not telling you anything that you don't already know. Okay, so the things about heat is something that you already know ever since you were born. All right, if there's temperature difference, there's going to be heat flow. The heat is always going to flow from hot to cold. If there's no temperature difference, there's no heat flow. The system is going to be in thermal equilibrium. All right, so if my coffee is hotter than the room temperature, it's going to cool down, right? Which means that the heat is going to flow from coffee to the room until there's no temperature difference. When they're at the same temperature, they will be in thermal equilibrium. There's not going to be any heat flow. So if there's no temperature difference, no heat flow. That becomes the Zeroth Law of Thermodynamics. So according to the zeroth law, if there's no temperature difference, there's no heat flow. You've measured the temperature here, you measured the temperature there, they're at the same temperature, there's no heat flow, which means that they're in thermal equilibrium. So this is known as the zeroth law of thermodynamics. All right, so speaking of the zeroth law of thermodynamics,
I'm talking about the thermometer he uses, the idea for which is...
Speaking of thermodynamics, it's always about temperature measurement. You measure temperature, check to see if there's temperature difference. If there is, there's heat flow. If there isn't, no heat flow. Everything is in thermal equilibrium. So speaking of measuring temperature, obviously we got three temperature scales: Fahrenheit, Celsius, and Kelvin.
snitched by its so-called inventor, the famous Dutch instrument maker, Gabriel Fahrenheit. Fahrenheit clears up the confusion created by everybody doing it a different way, with different scales on their instruments, so temperature is a matter of anybody's guess. Now, to start with, the way Fahrenheit makes his thermometer is nothing new. You just melt the end of a glass rod with a hole down the middle, and then blow down the hole to make the molten blob on the end expand into what will become the thermometer bulb that contains the mercury. Getting the mercury into the bulb's really nifty. Watch. You put the hot rod, bulb up, into the mercury, and the vacuum you made in there with the heat sucks the mercury up into the bulb. Okay, now for the absolutely lunatic way Fahrenheit comes up with a Fahrenheit scale, so hang in there. He starts with a scale, the bottom end of which is going to be the temperature of frozen ice, 0. He calls boiling water 60. 1/8 and 3/8 up the scale are freezing water, and a temperature of a healthy armpit. Are you still with me? Okay, make each degree 4 degrees, which turns freezing water from 7.5 to 30, and a healthy armpit to 90, but doesn't divide by 8. So make 30, 32, and 90, 96, and there you are, plus one last tweak. Clear as mud? I never said what Fahrenheit did would make any sense. Well, there's one thing I can explain, that armpit number. Remember I said he snitched the whole idea? In 1708, Fahrenheit visits Copenhagen and meets the ex-mayor of the city, one of those talented scientific amateurs the place is full of back then, guy by the name of Ole Rømer. Never heard of him? Thank Fahrenheit for that. See, the whole thermometer thing is Rømer's idea, so does the armpit number, and all the basic research. Fahrenheit kind of just turns up, takes notes of Ole Rømer's notes, and then nips back down south to Amsterdam. Not long after which, Ole Rømer's notes get destroyed in a terrible fire. Not long after which, it's Ole who? End of that sad tale. Okay, time for a quick catch-up.
All right, so that's the story of the Fahrenheit scale. And then we got the Kelvin scale. Okay, so regardless of which scale you're using, Fahrenheit or I'm surprised I don't know the details, Celsius scale. Both of them are based on the freezing as well as the boiling points of water. In the Celsius scale, the difference is broken into 100 smaller pieces. If it's the Fahrenheit scale, it's broken into 180 smaller pieces. Obviously, but Kelvin scale is a little bit different. The lowest point on the Kelvin scale is going to be absolute zero. And this is an extension of the Celsius scale that we're looking at. Okay. Idea comes from the previous lecture. Okay, so I spent a lot of time explaining it. When the temperature goes up, the pressure is going to go up because the molecules are moving faster and faster and faster. Obviously, the heat that you put into your system is going to go into the kinetic energy of the molecules, so the molecules are going to move faster and faster. And inside is a contained environment like the tires. When you put air into tires, the pressure is going to go up because you're increasing the number of molecules inside air, inside the tire. And then when the tires are heated up, the molecules are moving faster. As a result, the pressure is going to go up, which implies that the molecules are moving faster and faster. So the amount of heat that you put into the system is going to go into the kinetic energy of the molecules. When you cool down the tire, what's going to happen is the molecules are going to start to slow down. As a result, the tire pressure is going to start to reduce. And then when you start to cool it down further and further, the molecules are going to slow down. And then at absolute zero, the molecular motion is going to stop. The pressure is going to be zero. That tire is going to be 100% flat. So that's what it means. So on the Kelvin scale, the absolute zero represents the 0 Kelvin, which means that the relationship between kinetic energy of the molecules and the temperature is expressed in terms of the temperature scale, Kelvin scale. So as it so happens, according to the third law of thermodynamics, absolute zero cannot be reached. Why not? Okay, so we discussed the reasons for it during the previous lecture. I'm just going to give you a summary of it. The reason is because space is 3 Kelvin. Anything less than 3 Kelvin means there's going to be a temperature difference, which means that there's going to be a heat flow into that region. The second reason is because the temperature is related to the average kinetic energy of the molecules. So slow down the molecules, the temperature is going to go down. As the temperature goes down, the molecules will slow down. That's also either way you interpret it, both interpretations are correct. So the temperature is the measure of the average kinetic energy of the molecules. So zero Kelvin, the average kinetic energy of molecules will be 0. So which means that some of the molecules will have kinetic energies above 0, and some of the molecules will have kinetic energies less than 0. Less than 0 kinetic energy does not make any sense. You cannot have less than 0 kinetic energy. You cannot have negative kinetic energies because you cannot have a square of a negative number being negative. It's out of the question. And there's no such thing as negative mass, so which means that you cannot possibly reach absolute 0. The reason is because you cannot have 0 average kinetic energy. That's it. All right, so those are the two explanations that we end up getting from classical physics. So speaking of the temperature scales, we will have to do a bunch of conversions. All right, so Zeroth Law of Thermodynamics is the one that we're discussing. So if we have two regions at the same temperature, they will be in thermal equilibrium, which means that if there's no temperature difference, there's not going to be any heat flow. So measurement of temperature becomes essential in thermodynamics. Well, while we were measuring temperatures, we've got 3 international scales. The one that we use in the United States is the Fahrenheit scale. So the way to do it is you take the temperature in terms of the Fahrenheit scale, subtract 32 from it, that's the freezing temperature of water, and everything gets multiplied by 5/9. That's going to give you the temperature in terms of the Celsius scale. All right, so this becomes our conversion factor. We're getting this one. All right, so this is our Fahrenheit scale. We get the Kelvin scale out of the third law of thermodynamics. According to the third law, the absolute zero cannot be reached through any physical process for the reasons that I explained. All right, so as you start to reach absolute zero, as the temperature starts to go down, the pressure of the containment is going to go down. The reason is because the molecules start to slow down. And notice that at negative 273.15 Celsius, the absolute zero, the pressure is going to be 0. It's going to give you 0. So this temperature is taken to be absolute 0 on the Kelvin scale. All right, so absolute 0 implies that there's no molecular motion, so the average kinetic energy of the molecules would be 0. And absolute 0 cannot be reached because you cannot possibly have average 0 kinetic energy. That implies that some of the molecules will have negative kinetic energies, which simply cannot happen. The term itself does not make sense in classical physics. In classical physics, underlying classical physics. This is classical physics. The reason why I say classical physics, in modern physics, a lot of what's considered true in classical physics may or may not be true in modern physics. All right, so 100 years ago, 150 years ago, this is what people thought. That's the way they thought of heat. Okay, so we're just going with their interpretations right now. You guys are like 100 years behind the curve right now. This is classical physics. All right, so the conversion from the Celsius scale to the Kelvin scale is whatever the value you have on the Celsius scale at 273.50 into it, it's going to give you the Kelvin scale. So these are the conversion formulas that we get to use. All right, so let's get an idea. Let's get a sense for the human body temperature in terms of the Celsius scale as well as the Fahrenheit scale. All right, so 98.6 is an average human body temperature. Okay, so on the Fahrenheit scale. So if you want to convert it to Celsius and Kelvin, what do we come up with? All right, so if you want to convert it to Celsius, obviously there's the conversion formula. So for Fahrenheit, you will get to use 98.6. It's going to give you 37 degrees.
Hey, real quick, Professor, I had a question if you're available.
And then if we have a, that's the Celsius scale. I'm doing editing on the other computer. And this is on the Kelvin scale, and this is on the Celsius scale. Let's see. And then on the Kelvin scale, we end up getting 310 degrees. All right, just remember this 310 Kelvin. It should give you a bit of a reference point in terms of the stuff that we will discuss in the future.
This temperature scale once more to make it 32 degrees to 96, a difference of 64. Then using that thermometer, he measured the temperature of boiling water somewhat inaccurately, not very well, and he decided that it was 212 degrees. Later on, after he died, 212 degrees was defined to be the temperature of boiling water, and that shifted the temperature of the body a little bit. It's really 98.6 degrees. And that's how the Fahrenheit scale came into being. Now you might ask, which of these temperature scales is the best one? That's a silly question. The Kelvin scale, or absolute scale, is the one that's used by scientists. The Celsius scale is almost ideal for cooking because it's based on the temperature of boiling water in an open pot. And the Fahrenheit scale, which has 0 to 100 degrees as the range of normal weather temperatures, is almost perfect if you want to talk about the weather. Well, that's it. Don't forget your galoshes.
All right, so here, thermal expansion. Okay, this is a bit of an observation. So you got this Pyrex glass instead of regular glass for baking. So why did they use Pyrex instead of regular? Because the regular glass is simply going to break. It's going to crack. Okay, so why is it that Pyrex is going to work, but not the regular one? All right, let's take a look at the numbers, guys. It's related to expansion phenomenon. And then we'll take a look at the numbers shortly. All right, here's the original length. Here's the expanded length. So this is going to undergo this amount of expansion when you increase the temperature. So the temperature goes up, the expansion is going to go up. So how much it's going to expand is going to depend on how much the temperature is going to change. That's number one. So the length is going to increase. And what else is going to be related to it? So how much it's going to expand is going to depend on how much the temperature changes. And also it's going to depend on what the original length is. If the original length is small, it's going to expand this much. If the original length is doubled, expansion is going to be twice as large. Okay, so that's kind of common sense. So this is known as linear thermal expansion. So the amount of expansion is going to depend on the temperature difference. Also, it's going to depend on the original length. And it's also going to depend on the material itself. Okay, so this means proportional. I think we will get to use the same symbol for the expensivity, how much the material is going to expand. This is known as the linear expansivity or something. So delta L is the change in length. L is the initial length. This is the temperature change. This is known as the coefficient of linear expansion. Okay, so this is alpha. This one is proportionality. So the coefficient of linear expansion is going to depend on the material itself. Okay, in this case, the temperature change is going to be expressed in terms of Celsius. Even if it's Kelvin, 1 Kelvin is different. Temperature change in 1 Kelvin is the same as temperature change in 1 Celsius, so it's the same. All right, so coefficient of linear expansion, it's going to be an experimental value. It's going to depend on the material, so it's the measure of the tendency to expand or contract. So how much the material expands relative to its original length or temperature change is the coefficient of linear expansion. Okay, so it's a technical term, just get a feel for. Okay, so steel, copper, aluminum, lead, and the temperature difference will be the same for all of them. There's going to be a 50-degree change in temperature. Notice that the one that undergoes the most expansion is going to be lead in this case, so which means that the lead is going to have the largest coefficient of linear expansion in the setup. Okay, so lead is going to be here, steel is going to be here, so the lead is going to be 29. Okay, so 10 to the minus 6. Ignore that, just look at those numbers on the right, on the left. All right, so this is the coefficient of thermal expansion. We're looking at the numbers expressed in terms of millionth per Celsius that we got. Okay, so the couple of things, interesting things that I'm going to focus on in this one. Look at iron or steel, it's going to be 12. And what else? And take a look at concrete, it's also 12. Okay, so why is this important? It is important because the skeleton of each and every single concrete building is actually steel. If steel were to expand more than concrete, most buildings would just crack open. All right, they wouldn't last as long. All right, so they will expand and they will shrink at the same rate. So that's important for the survival of these buildings, the structures. Okay, so they expand at the same rate. When it's hot outside, they will contract at the same rate when it's cold outside. All right, so you got concrete and you got steel. All right, so you got the common glass and you got the Pyrex. Okay, so notice that the common glass expands a lot more and that's going to contract a lot. Now, Pyrex does not, so that's the reason why it doesn't crack as easily. Okay, so what else here, which is important? So I don't see anything else which is as important. The lead, 29, that's fine. What else? Brass, copper, gold. All right, liquids, there's nothing there. All right, so let's take a look at brass and take a look at steel. All right. Okay, so the brass is going to expand quite a bit. And it's going to contract quite a bit. If it expands real fast, if it's really hot outside, it's going to contract a lot more when it's cool outside versus steel. This is 19, steel is going to be 12. So when it's hot, when it's heated, notice this is what happens to the structure. When it's cooled down, this is what happens to the structure. All right, so in terms of a thermometer design, that's important. Okay, in terms of the indicator, which direction it moves. So brass is going to expand more. As a result, the indicator is going to move more, and then brass is going to contract more when it's cold. So the indicator is going to move in the opposite direction.
Easy. Different things expand different amounts. You see, these tiny, tiny basic particles are arranged slightly differently in different things. So every different thing expands a different amount when heated. Look, here are two strips of metal stuck together. One is steel and the other is brass. Let's heat them up, shall we? Now, don't try this at home. I'm a trained professional. Anybody got any marshmallows? Wieners? Who wants a s'more?
Hey, the strip is bending to one side.
Well, that's right, because one kind of metal is expanding more than the other. It's forcing the whole thing to move over, you see?
That's how a thermostat works, right?
Yes, that's right. Very good, my little thermostat man.
Mine works by turning the dial.
No, that's how you set it. You see, inside the thermostat in your house, you might have two strips of different metal. As the air in your house gets hotter or colder, the strips bend back and forth, pushing the on-off button on your furnace. Pretty neat, huh?
Samurai swordsmiths perfected a technology that few have ever matched. Their swords sliced cleanly through limbs. The samurai treated their blades with reverence. Some swords, they believed, had personalities of their own. Sadatoshi Gasan's family first began forging swords in the 13th century. It's scary how much of the swordsmith's personality appears as the sword is created. Not only do you have to polish your craft, but also your personality, because it too will appear in the sword. An evil sword maker would create an evil blade, so swordsmiths could only be men of the highest morals. These craftsmen faced an ancient dilemma. A sword must be hard enough to hold a sharp edge, but soft and flexible enough to absorb blows without breaking. Japanese sword makers were among the first to solve this dilemma, creating a blade that was both sharp and resilient, and they did it over 800 years ago. Their secret lay in their extraordinary ability to combine steels of different hardnesses. The swordsmith begins by making an extremely hard steel. Its hardness depends on its carbon content, which the master controls through hammering. He pounds and pounds until the carbon level is just right. Then he folds the steel. Each fold doubles the number of layers. Over a dozen folds create thousands of paper-thin layers in the metal. This hard steel will become the keen cutting edge. Next, he makes a softer, lower carbon steel. Now he joins the two together. The softer metal in the middle becomes the flexible core, while around it, he wraps the hard steel that can hold a razor-sharp edge. This is the breakthrough that made Japanese swords superior to all others. Hammering gradually draws the metals out into a single long blade. But he's not finished yet. Now the swordsmith takes the most difficult and magical step of all. He hardens the metal, fusing the steels together. He must raise the temperature of the entire blade to over 1500 degrees Fahrenheit, judging only by its hue in his darkened forge. The very last moment takes the most concentration. Is it going to be a good sword or a bad sword? Everything will be determined at this point. Now he will plunge the blade into cool water. If he miscalculates, and it's not at the right temperature, it will warp as soon as it hits the water. He will lose weeks or months of work. As the two steels cool, they contract at different rates, giving the sword its characteristic curved shape. It's a success. The sword made the samurai feared and famous. It weighed less than 3 pounds, about the same as a European blade. But its cutting edge was harder and sharper. It easily sliced through torsos and sent heads tumbling.
The previous documentary, the previous clip was interesting because evidently these people who built the or make the samurai swords end up using two different types of steel, and they don't expand at the same rate, and that's how they get the shape, the proper shape for the samurai blade.
Like many jet aircraft, it has 2 engines, 2 wings, and room for a couple of passengers. But stand back and watch out, because this bad bird flies faster than any other aircraft in the world. You're looking at the SR-71 Blackbird. Born during the Cold War, this high-speed spy plane could fly undetected from a record-setting 80,000 feet above ground and evade enemy tracking devices at speeds in excess of 2,000 miles per hour. Reaching these record heights and speeds required the latest state-of-the-art technology of the time.
Take an airplane and fly it at Mach 3 was a pretty good engineering feat.
Traveling at Mach 3 produced so much friction that temperatures on the exterior of the Blackbird reached a scorching 1,000 degrees.
All the systems had to take into consideration what heat was going to do to them, and so couldn't use normal fuel because normal fuel would cause an explosion.
On July 28, 1976, pilot Al George strapped into the cockpit of the SR-71 in an attempt to set the sustained aircraft speed record.
As you got faster and higher, the airplane was a little bit more sensitive. You could certainly tell that the airplane was operating at its limits.
At an altitude of 80,000 feet, Al leveled off and piloted the Blackbird through its designated course. Just over an hour later, he touched down and became the fastest man alive by flying the Blackbird to a record-setting 2,193 miles per hour. Although both Al and the SR-71 have retired from service, their record-setting flight still stands.
Okay, Mach 3. When you're going through air that fast, air friction becomes a factor, right? So what happens to the airplane? Heats up. Okay, so they talked about airplane heating up to about 1,000 degrees Fahrenheit. I suppose that's what they mean. And then they focus on the rocket fuel, but the thing to focus on is actually what happens to the airplane. When it's that hot, the airplane expands. We no longer have Concorde, for example. The Concorde is supersonic, was supersonic for commercial flight, and it would expand. All right, so the dimensions of Concorde is given here. The temperature is expressed in terms of 23 degrees Celsius. It's about 65 degrees Fahrenheit. And when it's supersonic, it could reach temperatures of 105 degrees Celsius. So I don't know, it's close to 200 degrees Fahrenheit, I suppose. So the coefficient of linear expansion is given. So find the amount by which the Concorde used to expand under the circumstances. All right, so the problems in this section are fairly straightforward. These are more exercises than problems. So the original length, initial temperature, here's the final temperature in terms of Celsius. So a coefficient of linear expansion is given. And this is for aluminum. So the aluminum is the outside, the skin. So how much of an expansion would it undergo in terms of meters, in terms of inches, in full flight while it's supersonic? So meters to feet, so the actual length is about 200 feet. That's what we got. 23 degrees Celsius is 75 degrees Fahrenheit. This is about 220 degrees Fahrenheit, just to get that impression. Originally, I got the problem from a book. I don't like using the metric units in setting up problems because we can't relate to these numbers. All right, so I decided to just convert it to the numbers that we can relate to. So that's the temperature change that it's going to undergo. All right, so it's straightforward. The temperature change is going to be expressed in terms of Celsius. The only thing that we have to do is just write out the temperature change and then plug the numbers in. So it's going to give us about 2 inches. So it would expand about 2 inches. So that 2 inches is actually factored into the design. All right, so just like Concorde factors that expansion into the design. Every time you build a structure like this, like the railroad rails, okay, so the expansion needs to be built into the engineering design. So you would have engine expansion slots if it's properly designed. If it's not properly designed, this is what you got. All right, guys, when you miss a lecture on engineering as well as physics, this is what happens. The quality of work becomes just like that. It becomes real expensive. The stuff you don't understand usually shows in physics and engineering. This is a properly designed system, and this is a system which is not properly designed. So the next question is, you need to have these expansion slots. So the question is, how much of a gap you need to have? So it depends on your assumption. Okay, so it depends on your assumption. So these guys are trying to build railroad tracks, obviously. So you need to know what the lowest temperature that you could get to in that region, and you need to know what the highest temperature is within that region every time you're designing these tracks. And then obviously you need to, if the highest temperature you could get is 100 degrees Celsius, for example, you need to add, probably add 20 more degrees to it. And then the lowest temperature is, I don't know, negative 20 degrees Celsius. I would make negative 40 or something. I would leave enough room to figure out what kind of gap I need to have for that section. All right, so in this case, the lowest temperature that you could get, evidently, it's going to be 0 degrees Celsius, so that's 32 degrees Fahrenheit. And then highest temperature that you could rise up to is going to be 42 degrees Celsius. And then the sections are going to be 12 meters long. So how much of an expansion slot or gap do we need for something like that? All right, so these are book problems. They're not exactly high quality, not like the problems that I tried to come up with. And evidently, I don't teach thermal very often. If I'm lucky, it's once a year. That's the reason why I didn't get a chance to upgrade the quality of the problems as yet. But this lecture needs work. All right, so let's write down whatever it is that we have. So the initial temperature is at 0 degrees. All right, so that's going to be the length of the gap that we need for the expansion slots. You can get up to 42 degrees Celsius. Original length is going to be 12 meters. For steel, it's going to be 12 times 10 to the minus 6 per centigrade. So that's what we got. So that's 32 degree Fahrenheit to 110 degree Fahrenheit. So that's the temperature range within that region. 12 meters is 40 feet. All right, so at least I'm trying to make the adjustments from a book problem to the numbers that we can understand. Once again, it's the same formula that we'll get to use. So which means that it's going to be a fraction of an inch, almost quarter of an inch gap needed within that region so that the rails don't buckle. All right, so speaking of the weird stuff that happens, let me show you an engineering disaster.
Almost immediately, the solar panels caused problems. Every 45 minutes, Hubble moved from sunlight to darkness with an abrupt temperature shift of hundreds of degrees. The sharp temperature changes caused the arrays to contract or expand, shaking the delicate machine for several minutes. Hubble had a bad case of the jitters and no way to get rid of them.
Okay, so what's causing the jitters? Okay, I got this from the engineering disasters on the History Channel, and this is a huge problem because when there's a temperature change, obviously the structure is going to expand and contract, so it causes expansions and contractions, and the whole system is vibrating. So what does that do to the image quality? Not so much. Okay, so that was a problem that no one considered before, so that's not a good thing. Okay, so we talked about linear expansion and contraction. We also have a volume expansion and contraction. When things are heated, they will expand. When they are cooled down, obviously they will shrink. Okay, just like before, we'll do a transition from linear to volume. That's what I'm going to do. So here's a linear expansion. And then what I'm going to do is I'm going to turn it into volume expansion. So here's a change in volume. It's going to depend on how much the volume is going to expand or contract. It's going to depend on the material itself. Okay, so this is known as the coefficient of volume expansion. This is the coefficient of linear expansion. It's going to depend on the original volume. It's going to depend on the temperature change. Okay, so coefficient of volume expansion is going to be 3 times the coefficient of linear expansion in general. So that's the rule that we get to use. All right, so the coefficient of volume expansion is how much the volume changes relative to the initial volume, which is right here, per temperature change. So it's just going to depend on the material itself. Okay, there isn't much which I find interesting here to focus on, except a little bit of physics. So what causes the volume expansion or thermal expansion? Okay, so I want you to kind of tie this up with the previous lecture. When things are heated, what happens to heat is energy that goes into the system. And that's the amount of energy that's going to go into the energy of kinetic energy of the molecules, right? So what's going to happen? The molecules are going to start to vibrate. Okay, so when they start to vibrate, the distance between these molecules will increase. As a result, there's going to be an expansion of the volume. Okay, so that explains it. Except that logic doesn't work so well with water. The water is, when water cools down, it expands. As a result, it becomes less dense. It's weird. And thanks to that anomaly, we got life here. Okay, why is that? Because the reason why that happens is the water is going to have the greatest density at 4 degrees. Okay, so when you start to reduce the temperature close to zero, what's going to happen is the top is going to be at 0 degrees, the bottom is going to be at 4 degrees. So which means that once you reach 4 degrees, the water is going to become dense, and dense water is going to start to sink down. The top could be 0 or less than 0. The bottom is going to be always at 4 degrees, and that's the ideal condition, obviously, to sustain life. If the water were to freeze in its entirety, there would be no life here on Earth. Let me put it that way. So that's an anomalous behavior of water. Is the reason why there's life. That's a weird thing. All right, that's the reason why in the universe we always look for places where there's water if you're looking for life. All right, so that's one of the conditions. So what's happening is at 0 degrees, the density of water is this much, and then what's going to happen is when you start to increase the temperature at 4 degrees, it becomes the densest, and then anything above that, the density is going to start to go down. So when you're freezing water at 4 degrees, it's going to become dense, the densest. So the 4-degree water, because it's denser than any other temperature, is going to start to sink. So at the bottom of every single water mass, the highest temperature is going to be 4 degrees. That's what it means. It's not going to be any lower than 4. All right, so now let's talk about the density of water. At 4 degrees, it's going to be the densest, obviously. So the question is why. Number one is it's related to the molecular structure of the water. And then, obviously, if you're looking at the molecular structure of ice, it looks like this. This is going to be at 0 degrees. And look at the space in between. The larger the space in between the molecules, the less dense it is, obviously. So which means that the ice is going to be less dense than the water. As soon as you break the connections, all right, so the molecules will be closer together. As a result, the density is simply going to go up. Okay, which means that you will have more molecules per volume once you break the molecular connection right there. Okay, another thing that we need to discuss is the Avogadro's number. This one is kind of weird. Okay, there's a conceptual way of approaching it, but evidently I decided to take a different route. Let's go along with this one. Okay, so let's just think of the gas inside the air inside the tire. Okay, so tire pressure is going to go up when you put air in it. The more air you put in it, the larger the pressure is. Okay, and you know the reason. The reason is because when you put air in it, you're increasing the number of molecules in the tire. Except molecules are not something that you can see. All right, you cannot really see these molecules directly. So you don't know if there are 10 molecules of air inside, a billion, trillion, quadrillion. We don't know the number. So what we do instead, we express the number of molecules inside the tire in terms of a unit called mole. 1 mole, it refers to this many particles, molecules, atoms, soccer balls, people. It doesn't matter. When you say 1 mole of something, you're talking about a certain number. All right, so the number of molecules will be expressed in terms of moles, number of moles that you got. Every single mole is a unit of measurement. It just measures 6.022 times 10 to the 23 particles or things or whatever. So just remember, mole is just a measurement of a huge number, and the number is going to be expressed in terms of this unit. All right, so 1 mole of any substance is going to have, this is known as the Avogadro's number. So the 1 mole of any substance is going to have the Avogadro's number of particles. All right. And if you're going with the book definition of it, it says 1 mole of any substance will contain as many particles as there are in atoms in 1 gram of isotope of carbon-12. All right, so the carbon-12, the isotope of carbon-12, 12 grams of it is going to contain this many particles in essence. Okay, this many carbon-12 atoms. Otherwise known as the Avogadro's number. So Na represents the Avogadro's number. Okay, so it's this many particles per mole. This is a standard number. I would just memorize it. Okay, I'm not sure if I have it on the formula sheet, just memorize it. All right, so another expression is 1 mole of any substance is the mass in terms of grams that's equal to the atomic mass of the substance. Okay, so the question is, what does that mean? All right, so lowercase n is going to represent the number of moles. Okay, so this is the number of molecules that you have, total number of molecules that you have, which is going to be expressed in terms of the Avogadro's number. Okay, so in terms of the example that I was giving you, so capital N is going to represent the total number of air molecules contained within the tire itself, and then you will express this in terms of the Avogadro's number. So this becomes the total number of moles. Or there's a second way of expressing it, because you know there's no way you can count the number of molecules. You never know. The number of molecules cannot be counted. Okay, so if given the fact that you cannot count the number of molecules, how would you know how many moles contained within the tire itself? lucky for us, there's a way to compute that. Okay, the way we compute it is this. You take a look at the mass of the air inside the tire and divide it by the atomic mass of the air inside the tire. That's what we do. All right, so total number of particles, there's no way to count that sort of stuff. And the total number of particles or molecules in our case will be expressed in terms of the total number of moles. For us to be able to do that, we need to look at the total mass and divide it by its atomic mass. Okay, so the total mass and the atomic mass in this case is going to, atomic mass is going to be expressed in terms of grams per mole. So you will get to express the total mass in terms of grams. Okay, so going back to our example, we just repeat what I said. If you want to know the number of moles of gas molecules inside the tire, you need to measure the mass of the air inside, take a look at the total mass of the air inside, and divide it by the atomic mass of that air per mole. That's it. Okay, this is measurable, and this is something you can look up. All right, of course, I made it too easy. You just have to kind of remember the ratios of the molecules inside air, like it's going to be 78% nitrogen, and then you got 21% oxygen, and then you got other small percentages of this and that. And then you need to know their atomic masses. As long as you know the total, as long as you know the total mass and the ratios of individual masses, then it works out. Okay, so that's how it is now. Atomic mass is something that you get from the periodic table. I had to say that, periodic table. Okay, so that's pretty much just this. This is the formula that we will get to use. All right, just remember, you need to know the total mass divided by the atomic mass. That's going to give you n. And if you take n multiplied by the Avogadro's number, it's going to give you the total number of molecules inside the tire. Okay, so the total number of molecules is not something you can measure, but you can compute. Okay? Everything comes out of this green formula. All right, so if n is 1, okay, so why am I doing that? It's got to be from a book somewhere. And it's lost interest in that one. Evidently, it had a promising start. It didn't go anywhere. All right, so this is problem number 8. It's about the diamond, the whole diamond. Gotcha. You can almost see this, but not quite. Okay, so which is almost pure carbon. It's got a mass expressed in terms of carats. And then we have a ruby, which is also expressed in terms of carats. It's primarily aluminum oxide. It's a combination of aluminum and oxygen of some sort. So evidently 1 carat is the same as 0.2 of a gram. I say evidently, that's usually not something I would know or remember. So let's figure out the number of carbon atoms in the diamond. I think I'm just going to do A. These are the same as A, but evidently I'm not going to be interested. Okay, so here's the actual mass of this diamond expressed in terms of carats. Okay, so how many atoms contained inside of it? All right, so that's a good example. So the carats is going to be expressed in terms of grams. 1 carat is 0.2 of a gram. All right, and then the next thing we need to do is we need to figure out the number of moles that we can get out of it. So take the total mass divided by the atomic mass of carbon in terms of grams per mole, and that should give us n. And then from that, you can figure out capital N. So because we have a sequence of formulas like that, we can just isolate n from here on this thing. We know the Avogadro's number, so look at the ratio and multiply by the Avogadro's number. Okay, so the atomic mass of carbon is 12 grams per mole. We got the Avogadro's number. Plug the numbers in and multiply. So it's got, man, that's almost 4.5 million times million times million. This is almost 45 million times million times million times million. 45. No, it's 0.45 times million times million times million times million atoms. Okay, so that's a lot of atoms. So that's a computation. Okay, so, okay, you guys took this stuff from chemistry, right? Pong. All right, so it's a lot of chemistry repeating. I just want to make sure that you guys kind of know the background stuff because chemists are the ones who kind of develop the, this is not going to be as brutal, guys, because physics is nicer. I'm working on your understanding of it. Okay, so Robert Boyle, let's talk about the ideal gas form. Okay, what is an ideal gas? Ideal gas is not a real gas. It's an idealized form of gas. It's composed of molecules, and the molecules are point-like. They're not interacting in any way except they collide with each other. No electrostatic forces. That's definitely true. It's cuter. No electricity. Physics is 100 times more difficult, but at least you get a good understanding. All right, so ideal gas is you got point particles. There's no gravitational forces, electrostatic forces. If they if they interact through collisions, and that's it. Okay. It's not. It's an approximation of a real gas. Okay, so that's what we got. This one, ideal gas law, is straightforward. I'm hoping that it's really straightforward. So the pressure versus volume. Okay, so by squeezing it, you increase the pressure. Obviously, that's what it means. Okay, isotherm, which means temperature is going to be constant. By squeezing it, you're increasing the volume. All right, so the pressure is going to depend on the volume. That's weird. And proof. I don't like to like this setup, but let's go with that. I want to come up with it. I like to come at it from a different perspective. All right, so pressure and volume are going to be inversely related. So by increasing the volume, you will reduce the pressure. By reducing the volume, you will increase the pressure. Okay, let's go with boil at constant temperature. So if the temperature is constant, all right, the pressure is going to depend on inversely related to the volume. So you reduce the volume, you squeeze some, the pressure is going to go up, and then you increase the volume, the pressure is going to go down. It's very simplistic. I didn't want to approach it from this perspective, but let's go along with it. Okay. All right, so this is known as the Boyle's law. Man, this guy just discovered something 200-300 years ago. It's very simplistic. Okay, so this is an isotherm, meaning that the temperature is going to be constant on this curve. So by reducing the volume, you can increase the pressure. By increasing the volume, you reduce the pressure. That's it. And so this is at 20 degrees, this is at 50 degrees. You can repeat the same thing at a different temperature. And that's it. I'm just doing this so that you guys get used to the terminology. This is not the most exciting stuff, but you kind of got it. Okay, so what else do we have here? Okay, so by increasing the temperature, you can increase the pressure. We discussed that, the tire pressure. When the tires are heated, the pressure is going to go up because the molecules inside are moving faster. All right, so you got a piston here, and you got a piston here, and then you got this volume, which is filled with gas. So if you heat up the gas, the pressure is going to go up on the inside. Okay. I think that's what becomes the Charles's law. Somebody has to get credit for this simple idea. Okay, damn. All right, every single thing that you can think of, every single simple thing that you can think of, somebody actually thought of it a couple of years ago. Okay, so temperature goes up, the pressure goes up. All right, so the temperature goes up, the pressure goes up. And out of this, we end up getting the third law of thermodynamics. So Charles gets that idea. All right, hopefully this is my commonsensical approach to physics. Or is it just a book knowledge? Okay, so ideal gas law. Okay, so I'm re-articulating the meaning of an ideal gas. So we got this non-interacting point particles. These are the molecules. Okay, non-interacting meaning that there's no gravitational force to speak of, no electrostatic forces, and the density of the gas is so low that there are no collisions. Even if there are collisions, these are perfectly elastic collisions. So extremely low density. Chances of any sort of collisions is extremely low. If they interact at all, the momentum is going to be conserved. These are, as well as the kinetic energy, so elastic collisions. So these are the built-in assumptions for the ideal gas law. All right, so remember, momentum is going to be constant, kinetic energy is going to be constant. There's nothing else. These are the assumptions. All right, so here's what we know so far. Okay, finally, my commonsensical approach as opposed to the book knowledge. Okay, so temperature goes up to Kelvin temperature. Molecules are moving faster. Because they're moving faster, they get more kinetic energy. And because the kinetic energy is large, the pressure is going to be large. Okay, so these molecules are inside some kind of a container like the car tires. As temperature goes up, the molecules are moving faster. They got larger kinetic energies as a result. So the pressure that they will apply, exert, generate will be extremely high. So pressure is going to be directly related to temperature. So temperature goes up, the pressure goes up. This becomes the Charles's law. And the tire pressure is going to also depend on the number of molecules inside. Okay, so I'm just giving you commonsensical physics. So temperature goes up, the pressure goes up. You increase the number, put more gas into, put more air into the tires, so the pressure is going to go up. All right, so if you reduce the volume, once again, the pressure is going to go up. All right, this is the Boyle's law, Charles's law, and this is common sense. Okay, so everything comes out of that little thing that happens inside the tire. All right, so if we put more air into the tire, pressure goes up. Increase the temperature, molecules are moving faster, kinetic energy goes up, the pressure goes up. And then if you squeeze the tire, the pressure is going to go up. Okay, so that's how it is. Okay, so everything that we discussed can be expressed in terms of this single formula. So pressure is going to be directly proportional to the number of molecules. is going to be directly proportional to the Kelvin temperature. It's going to be inversely proportional to volume. So that requires some kind of a proportionality constant in order to turn this into a formula. So that proportionality constant that we will get to use is going to be the magical letter from an alphabet, which is known as K. I was going for R, but let's settle on K for now. All right, so K happens to be a proportionality constant. I hate that term, but let's go on with that. So that we can take these relationships and then turn them into an equation. And K, otherwise known as the Boltzmann's constant. Right, so it's an experimental number. It's a small number, expressed in terms of joules per Kelvin. And Boltzmann is the name of someone that we will discuss. Right, this guy did something real important. This guy is the guy who introduced the atomic theory into physics. And when he did, no one believed in the existence of atoms. I'm talking about the beginning of the 20th century. Most physicists and chemists were perfectly okay with treating atoms like mathematical constructs, but they didn't believe that this stuff was real. Right? They didn't believe that this stuff was real. And Boltzmann was the one who believed that this stuff was real. And this is the guy who came up with the kinetic theory of gases, in essence. This is the guy who said the temperature is directly related to the kinetic energy of the molecules. And then he came up with something that we refer to as statistical mechanics today. All right, so we'll deal with them later on. So in honor of Boltzmann, this is known as the Boltzmann's constant. So what do we know? We know that it's impossible to count the number of molecules directly. Okay, so as a result, we end up using the number of moles. And then, all right, so if you multiply the number of moles with the Avogadro's number, it's going to give you the total number of molecules. So what we will do is we'll just do a back substitution here. And there's a reason for it, because I want to come up with a second formula for the ideal gas law. Okay, so here's the Avogadro's number. It's a constant. Here's the second constant. That's the Boltzmann's constant. Okay, so instead of using two separate constants, so we will multiply these two together and come up with a single constant. Physics is exciting. I don't know if it's physicists or chemists came up with this, but this is just too nutty. Okay, so the product of the Avogadro's number and the Boltzmann's constant is going to give us a different constant, which is known as the ideal gas constant. All right, so this happens to be a smaller number, expressed in terms of joules per mole per Kelvin. It's the ideal gas constant. So this whole term is going to become capital R. So you end up getting this expression that you guys will remember from chemistry, PV nerved. All right, so this is known as the ideal gas law. So you got the pressure, the volume on the left-hand side. On the right-hand side, you have the number of moles. You got the ideal gas constant, R times T. This is the Kelvin temperature, so just remember that. And everything that we did, I could have come up with this on my own. Oh my God, there's nothing here. Forget Charles and forget Boros. This is the sort of physics you can come up with while you're watching commercials on TV. All right, this is really straightforward. The only thing you have to think of is the air contained inside the car tires. All right, so put more air in it, the pressure is going to go up. Increase the temperature, molecules are moving faster, kinetic energy is going to go up, the pressure is going to go up. So that's included here. Squeeze the tire, the pressure is going to go up. That's it. And then come up with a proportionality constant. You can call it any letter you want. You can call it K because I'm Ken, or you can call it K because it's Boltzmann. I don't care. I don't care what the letter is. And because you cannot measure N directly, okay, so you can express this in terms of the number of moles is something that you can calculate. And when you do that, obviously, you end up introducing two constants, you multiply them together, and then come up with a different constant. And then this is going to give you the famous formula PV equals nRT, and that's it. Okay, so that's the commonsensical way of doing physics. Forget who did what. You could sit down and figure this out on your own, and then feel good about it. All right, it's not that complicated. All right, exercise problem number 9, man. Hey, what's this? Let's check to see how cute this is. This is not that complicated. Something about the lungs. And so what do we have? We've got tiny sacs of air inside the lungs. Absolute pressure is going to be, this is 1 atmospheric pressure, it's 100,000 Pascal. Alveoli is the name of these sacs, evidently, and that's from where the oxygen enters the blood. So the radius of each sac is given in terms of millimeters. We got 14% oxygen, which is contained inside alveoli. It should be 21, but 21 or 22, I don't know what the number is. It's somewhat smaller amount than the fresh air for some reason. I don't know why. Once again, a simple problem. We will have to assume that the air behaves like ideal gas, which is a good thing, so we can use PV and RT. All right, so the body temperature is 310. So they find the number of oxygen molecules in one single stack. All right, so that's what we need to do. Okay, so it's not bad. All right, so we got the pressure. Pascal is the proper unit. I'm good with that. We can figure out the volume of this. All right, radius is given. So assuming that this thing is spherical, obviously, 14% of the air is going to be oxygen. So we got the percentage of it that we can use, and we also have the body temperature. Okay, so figure out the number of molecules in one single stack. So P pressure. This should be, what is it? It should be 100. It's not 10,000. It's 100. Yeah, it should be 100,000. Okay, well, welcome to my reality, not paying attention. All right, so the radius is given. 14% oxygen of total number of molecules. Temperature is in terms of Kelvin, so the number of molecules. All right, so I'm making a correction now. Okay, I'm happy with that. This is happening during the lecture. This is about 15 psi, pounds per square inch. It's 14.7 pounds per square inch outside pressure. All right, so this is the average human body temperature. Okay, so just solve it for n. Okay, so when you solve for n, it's going to give you the total number of molecules inside. Okay, so the volume of the stack volume, this is assumed to be spherical. So here's the volume of the sphere. We'll do a back substitution. Okay, I don't see any cancellation, so I just simplify it. Simplify it. All right, and okay, so what did I do? I don't know. Okay, so this is the total number. Okay, so what we need is we need 14% of it, so multiply it by 0.14. And then just plug the numbers in. And it should give us a number in terms of, it's 26 trillion molecules within one single stack. 26 trillion oxygen molecules. Okay, that wasn't that bad.